This tutorial will demonstrate how to perform a hypothesis test which corresponds to the second form of generalization discussed in class. So, generalization hypothesis test. We can test hypotheses for averages and percent, but what exactly are these hypotheses? When we say hypothesis test within the context of the textbook, we are referring to three hypotheses. If a population parameter, which can be a mean or a proportion, is equal to a number, if it is greater than a number, or if it is less than a number. So let's see how it works. I see this variable here called number of people in household. It's a metric variable. And I assume that usually in household there are two parents and a child, or if there are two kids, perhaps one is in college, or there are only the parents and it's an empty nesters family. And anyway, my initial assumption is that the number of people in household equals 3. That's my initial guess. So let's see if I'm right or if I'm wrong. To do so, I need to test hypotheses. Number of people in household is a metric variable, therefore I need to test hypothesis for average. Going to generalization hypothesis test average. I click it, I select number of people in household, and I want to compare this the number of people in household to 3. I just tap it, I enter this number, then click OK. This is the output, and this output starts with a table summarizing what was tested. The table says that we compared the number of people in household, in this sample consisting of 1,000 people, to 3. This is the number which I entered. And the number of people living in household according to the sample is 2.2. However, we need to see if this 2.2 is statistically different from 3 on population level. That's why we test the hypothesis. Even the good thing about XL Data Analyst is that even if you don't know what you are testing or the notations about the 3 hypotheses, you still can read, understand the result because it's written in plain English. The first output here tests the hypothesis if the number of people in household is equal to 3, and we see that it is not supported. The second statement is the result of a test that the number of people living in household is greater than 3. It is not supported. And the final output, the final result, is the result of testing a hypothesis that the number of people in household are less than 3, and we see that it is supported. So even without not knowing the notation of hypothesis, we still can understand what happened. But let's provide some more insights into this this output. It's important to understand what actually happened. The statistical tests, the result from a statistical test in XL Data Analyst usually are provided with shaded background. So these are the results from statistical test. Probably the most important value in statistical in testing a hypothesis is the p-value or significance. SPSS and XL Data Analyst annotate p-value with significance SIG, which is essentially equivalent to p-value. The significance level is very important. I'm going to highlight it in red because it is the trigger which is used to accept or reject the null hypothesis. In our case, the significance level is very small. Actually, it's smaller than 0.05. Therefore, because it is smaller than 0.05, we reject the null hypothesis. In the first case, the null hypothesis was that the mean is equal to 3. The alternative hypothesis is that the mean is not equal to 3. Because we have a significance level which is below 0.05, we reject the null hypothesis for equality. So actually, the alternative is accepted, which means that the mean, the number of people in household is different than 3. This statistical output relates only for this hypothesis for equality. The statistical output for the other two hypotheses is not depicted. I should mention that when testing hypothesis for equality, we use two-tail test, and when we test the directional hypothesis for greater than or less than, we use one-tail test. Again, the statistical output is based only for two-tail test corresponding to the hypothesis which tests for equality. Although testing only the first hypothesis usually is enough to infer the direction, SPSS, XL Data Analyst still tests the other two hypotheses. Let's use just the result from the first hypothesis to see if we can determine the direction of the relationship. Again, the significance level is less than 0.05. We reject the null hypothesis for being equal to 3, which means that the number of people in the household actually is different from 3. If it is different from 3, is it greater than 3 or less than 3? Just by looking into these numbers, we see that the sample average is 2.2, but we compare it to 3, so we can conclude that if it is different from 3, then it must be less than 3. And we see this confirmation here that the hypothesis for less than hypothesized average actually is supported. And this is how we test hypothesis for average, for averages. Let's do one more. Let's say, again, I will use the proportion for buying a standard size electric auto within 3 years. I would like, as a researcher, to see if the probability of buying a standard size electric auto within 3 years, I would like to see if it is equal to 30% probability. To see if this probability is equal to 30%, I need to test the hypothesis and go to generalize, hypothesis test, average. I select this probability and compare it to 30%. 30. Click OK. And the table indicates that we compare the probability of buying a standard size electric auto within 3 years to 30%. The sample average, again, the sample average is 34.6, but we still need to test if 34.6 is statistically different from 30. We see that our significance level is very small, it's below 0.05, therefore we reject the null hypothesis for which is that it is equal to 30, and accept the alternative which states that the average is different from 30. Well, if it is different from 30, is it greater than or less than? Well, we see that the sample average actually is greater than 30, and actually we see that the hypothesis for being greater than 30, which is the hypothesized average, is supported. So I would say that the second and the third hypothesis may be skipped. This is exactly what happens in SPSS. Not that this is the most precise statistical approach. Again, there is difference between one-tail and two-tail test, but for practical significance, not for statistical, for practical significance, it's more than enough to use only the hypothesis which tests for equality. If that's it, let's try another hypothesis for proportions. Let's say I would like to compare, I would like to see if the proportion of unmarried people is equal to 52%. I read somewhere that unmarried people are more than married people, and I believe that there are, let's say, about 52%. So I'm going to compare the proportion of unmarried people to 52. Because this is a categorical variable, I need to select percent. Now, marital status, unmarried, and I want to compare it to 52. So let's see if it is equal to 52, greater than 52, or less than 52%. Okay, what we see here actually is very interesting. We see that the significance level is 0.04, just a little bit below 0.05, which is enough to reject the null hypothesis for equality. In other words, we now are confident this significance level indicates that 48.7 is statistically significantly different from 52%. So these two are different, statistically different. And actually, the sample percent is less than the hypothesized average, which indicates that the proportion of unmarried people actually is less than 52%. And when we look down in the final output, in the third results, which usually tests a hypothesis of being less than hypothesized average, we see that it is supported. And this is how it works. Well, let's play a little bit with this result. I have the feeling that if I select 50% here, I'm not going to get significance here. So I go back and perform the test again. I still want to compare the proportion of unmarried people, but this time let's compare it to, let's say, 51. Okay, now I compared the proportion of unmarried people to 51. Looking at the significance level, I see that it is larger than 0.05, which means that I cannot reject the hypothesis of equality. In other words, the proportion of unmarried people is not statistically different from 51%. Well, how is this possible? Well, don't forget that 48.7 is the proportion based on a sample. But when we compare it at the population level, because the hypothesis tests are for population level, actually we are on population level, we have a confidence interval. We don't have just one, we don't just have a number. That's why it is possible 48.7 to be statistically different from 51%. Here is one demonstration quickly. Let's calculate the confidence interval for unmarried people. And you see that 51% is within the confidence interval. So I'm going to calculate the confidence interval for the proportion of unmarried people. And as expected, and as expected, 51 is within the confidence interval. So everything which is inside the confidence interval is a possible value on a population level. That's why it is not statistically different. So this is how we calculate hypothesis tests for equality greater than or less than a number.